Okay, good morning all of you. My screen is visible?
Yes, sir.
Okay. We'll see that just continuation of previous class. We stopped here in the parallel operation. As you are aware that in a parallel operation we need to meet the current demand. We are connecting number of SCRs in parallel. That part is some of the portion is completed, but now the problem is the temperature rises in the
Sir,
yeah. Hello.
your voice is not clear, sir.
Voice is not clear.
There's some
Hello.
disturbance, sir.
Just a minute. Now it is okay. Hello.
Yes, sir.
Okay. We can see this. Whenever if any disturbance comes, let me know, ma.
Okay, sir.
Here we can see that temperature will rises in a SCR. In that case, what will happen? The devices consequently will failure because one of the SCR will share the more current that leads SCR, that particular SCR will damage, and consequently other SCRs will be overloaded, and finally the total string is going to be damaged. So to overcome the drawback, what we are doing is we have to keep that heat sinks. The function of heat sink is it will suppress the temperature, or it will not allow to rise the temperature. So in that case, we have see that one is unequal current distribution in a parallel unit is also caused by the inductive effect of current carrying inductor. Suppose if you consider these are the three SCRs, current carrying conductor will be like this. Then what will happen? There is a linkage of the flux linkage in the middle conductor is more when compared to others, because this is second conductor is near to the first one as well as the third one. That's why flux linkage will be more. To again, one of the conductor is carry the flux linkage is more, that inductance will be more. If the inductance is more, automatically current shared by that particular conductor will be less. Then obviously other conductor will overload. That's why to overcome the drawback, what we are doing is we are using as a symmetrical arrangement. Then what will happen? All the three conductors distances are same. When unsymmetrical case, the middle conductor will be more inductance, no. But to overcome the drawback, we have to go for as a sequence, or you can say that symmetrical configuration. So that's what I mentioned. In this case, there is unsymmetrical case, less current will flow through the middle SCR compared to other one. That is a unequal current distribution is taking place. To overcome that, we have to go for as a figure B, that will be as a symmetrical configuration. Now that is one thing, and other thing is also there. Forcibly we can use the resistance in series with the each SCR. Then what will happen? That is external resistance. There is a forward voltage drop across each arm should be the equal. So if you place one resistor in this each SCR, then voltage drop across that each SCR will be the equal. But you can see that both are in parallel. VT1 voltage across the SCR1 plus whatever current is passing through the SCR1, that is IT1 or I1, into what is the resistance, internal resistance of that junction of thyristor 1, and plus additional resistance is R1, that is equal to this one. So what we are equating that two branches, this one and is equal to this one, such a way that we have to find what is the RT, this R1 and R2 values. You can see that VT1 voltage across this SCR plus current shared by that line into R1, this is R1, plus RT1 is a internal resistance of that particular SCR. That is equal to this. If we equate this fashion, so now preferably R1 is equal to R2 is equal to R. RT1 and RT2 are the junction resistance of the SCRs. That way also you can make it equal sharing. And what is the drawback in that is if we use as a resistor, current is passed through that resistance because each SCR is going to share. Current passed through that resistance leads to the power dissipation. So that's why preferably we don't use resistance connection in series with the SCR. But alternate option is there. You can use as a mutual coupling inductor. So in this case, we can able to make current sharing between these two SCRs will be equal. If any case, one of the SCR is trying to carry the more current, then automatically, because both are mutually coupled, and this other inductor will offer less impedance, then automatically other SCR also try to carry the more current. It will balance the current sharing. Our second SCR is trying to carry more current, and first SCR impedance offered by that will be as a less, and again it will divert the current. So that way we can make use of this. This is the preferable one to make current shared by the each SCR to make it as a same. That's what I mentioned here. Parallel connection of SCR with mutual coupling of inductor we use. Then whenever current flows through the T1 and T2 are same, then IT1 is equal to I22. So voltage drop across the inductor is 0 in normal condition if both SCRs are sharing equally because of the mutual cancellation of the inductance EMF. But if any case, we can see that if current flows through the thyristor 1 is greater than the thyristor 2 or vice versa also, the inductor induced EMF in a coil is directly proportional to the unbalanced current. So in that case, what will happen? Current flows through the inductor 1 decreases, but the current flows through the coil 2 increases. Hence, there is a tendency to share the current equally. That's what I explained just now. So anyone, either suppose thyristor 2 is trying to carry more current, automatically one is going to be drop down that impedance and it will share the other current. So that way we can see that. So now we can see some of the problems related to series and parallel operation. They see the question, a thyristor string is made of number of SCR connected in series and parallel. There is a string we need to connect either in the series fashion or in parallel fashion. So depends on our requirement to connected in series and parallel. The string has voltage and current rating is given. 11 kV voltage rating, 4 kiloamperes is a current rating. And each available SCR with you is this much voltage, 1800 volts and 1000 ampere of current. But our demand is what? 11 kV demand I need to meet, and other case 4 kiloamperes current demand I need to meet. But available SCR with you is only 1800 volts. But to meet 11 kV, how many SCRs need to connected in series? And other version, my demand is 4 kiloamperes, but I have 1 kiloampere of SCR or 1000 ampere of SCR. How many we need to connected in parallel to meet as a 4 kiloamperes demand? Now the string efficiency is 90%, so it is also given. Number of SCRs in series and parallel we need to find. Then the value of A and B will be, we have to find. A means let it be as a series and B is a parallel respectively. They mention, otherwise NS and NP also you can use it. NS is the number of SCR connected in series and number of SCR connected in parallel. Now, as you are aware in the previous class, string efficiency formula, I mentioned efficiency formula, actual voltage. Suppose if I want to find series means use the voltage, parallel means use the current, that's it. So, actual voltage rating of the whole string divided by number of SCRs are in series into 1 SCR voltage rating. That is the formula for string efficiency. So, in this case, what is the whole string? 11 kV. This is our demand, or to meet that will be as a 11 kV, and into 10 cube divided by, I want to know how many SCRs are in series, that I don't know, let it be A. And what is the voltage rating of one SCR? That will be 1800 volts. And what is the string efficiency is given? That is equal to 90%. So let it be 0.9. That's all. This is one equation. You just substitute the data, we'll get what is the A value. And what is the B value? Same thing, you make use of current rating. Then what efficiency is given? String efficiency is 0.9, 90%. And current rating is given 4 kiloamperes, means whole string. Actual current rating of the whole string divided by number of SCRs are in parallel into 1 SCR current rating. What is 1 SCR current rating? 1000 amperes. That's all. You will get A and B. So the problem is over. That's all. So just if you know the formula, you can just substitute. That's what I mentioned. Here the thing is, it is a number. Actually 4.7 SCRs won't be there. Even 4.1 also you make it as a 5 or like that. 6.7 not be there. So what we have to do? 7 SCRs we have to connect it in series according to our formula. And similarly for parallel case, can use 0.9 into this numerator is not 1000, it is a 4000 divided by B into 1000. So that will give as a 5 SCRs are in parallel. You just check it calculation if anything, in whether they used something here is a 4 or not. Now total string is 4 kiloamperes, that's why 4000 numerator will be. So this 4.9 SCRs means 5 SCRs you have to connect it in parallel to meet the this much demand. So because of the efficiency is 90%, little bit more number of SCRs you have to connect. Otherwise it will be 4 is sufficient. Because it is efficiency is only 0.9 it is given, no, that's the problem. It will get more number like this. This is one problem. And we'll see other one. There is a figure is given like this. It is a paralleling of SCRs. Rated 400 amperes, sharing a load current. Current through thyristor 2 is 180 amperes. What is the current through thyristor T1? So the question is, how much current passed through the thyristor 1? But total current is what? 400 amperes. But how much current passed through the thyristor 2? It is given as a 180 amperes. Now we can see this. These are not same. That's why automatically the current shared by one SCR will differ. It will not be equal based on this drop. The resistor is already connected. Now the formula will be like this. You can see that AB current into that resistance, and from that we'll get what is the IT1, and that will give as a 150 amperes. So same as in the explanation, if I connect as a resistor forcibly, current shared by the device going to be equal. So here proportionately it is going to be shared. So that's the reason one is a 180, another one is a 150, and that is going to be shared across this. And now there is a 200 amperes thyristor is to be operated in parallel with 300 ampere thyristor. Now we can see the current rating of the each SCR is not same. One SCR current rating is 200, other one is 300. Then the sharing also proportionately it is going to be shared. Now proportionate in the sense by default it is equal sharing only with respect to their capacity. But if you connect, one is 1000 ampere SCR, another one is 100 ampere SCR, total is 200, you cannot share equally because that capacity is not that much. No, based on their capacity, proportionately it is going to be shared. And the on-state voltage drop is given, that is a VT1 is 1.5, VT2 is a 1.2 volts. What is the value of resistance? Means R, we need to connect it in series with each thyristor, because they mention 2 thyristor, and this is a thyristor 1 resistor we need to connect. Similar fashion, thyristor 2, but their ratings are different. This is a thyristor 2, and then the question is, what is the resistance value? But what they mention is current rating of SCR1 is different, SCR2 is different. Combinedly, it is going to be shared. This I is given as a 500, and drop across this one is mentioned 1.5. This one is mentioned 1.2, and use your equation. Previous paralleling I given one relation. You just use that relation, you'll get it. What is the value of R? It is straight away question. You can see this. This is a VT1 plus current IT1 into resistance, that is equal to VT2 plus IT2 means current shared by I2 into R. Then from this unknown parameter is only R. Then this much resistor we need to connect in series with the SCR. And there is another problem, rated 200 volts, because these problems are very important. All direct straight away question, there is no indirect. Whatever data is given and direct substitution in the formula. But you must identify what is the formula required for that. Only formula remember, you can easily solve this problem. Operating voltage of a string is 600 volts. Determine derating factor of the string. Now we can see that derating factor is equal to 1 minus string efficiency. So this is the formula. String efficiency means that what is the voltage, because here they given as a voltage, that is the reason we use it as a voltage rating. And we can mention 600 volts whole string divided by number of, you can see that number of SCRs are mentioned in problem, 4 thyristors, each SCR rating is 200. Then what is your string efficiency? Once you know the string efficiency, the rating factor is equal to 1 minus string efficiency. Hello, am I audible?
It's not clear, sir.
Voice is not clear?
Now it is okay, sir.
Okay. You just ask me at any time. If any disturbance comes, let me know. I will rectify here. Something, there is signal problem today, I think so. Okay, you can see string efficiency formula is known to you. Actual voltage rating of whole string. The mentioned voltage rating is 600, not a 0.6. It is 600 volts divided by 4 SCRs are in series. That's why I mentioned 4 here. And other one, you can see that 1 SCR rating, that is given 200 volts. Then we'll get it as a 0.75 is our string efficiency. But the question is determine derating factor. So what is the derating factor? That is 1 minus string efficiency. Therefore, 0.2 is our derating factor. 0.2 means here derating factor is based on the reliability of the what you can say that the reliability of the string. The rating factor will give the reliability, and string efficiency is utilization. So that is the problem. We asked derating factor calculation is 1 minus string efficiency. Now there is another problem. A string of n parallel SCRs is operating 75 kiloamperes. The rating of each SCR is 1 kiloampere. If derating factor is 0.1, then how many SCRs are connected in parallel? Now you can solve any one of you. It is easy. What is the formula? Anybody? What is the formula I have to use? N I have to calculate. N means here paralleling the SCRs. Now derating factor is equal to, because they mention derating factor of the string is a 0.1. Derating factor is equal to 1 minus string efficiency. And what is the derating factor? 0.1. That is equal to 1 minus, what is string efficiency? Actual volt here current, because parallel, no? Actual current rating of the whole string. Then what is the current rating of whole string? 72 into 10 cube divided by n is unknown, number of SCRs are in parallel, into 1 SCR current rating, that is a 1 into 10 cube. That's all. So we can easily calculate what is the number of SCRs need to connected in parallel if derating factor is 0.1. Same thing you try to calculate if derating factor is 0.2. That means we are increasing the reliability. If derating factor is increases, then what will happen? Same rating, same operation, number of SCRs connected in parallel will increases, because you want to increase the reliability, then automatically number of SCRs are connected in parallel also going to increase. That is the derating factor effect. That's what I mentioned here. You can see that 0.9 means 1 minus string efficiency. 1 minus string efficiency is our derating factor, and n is a unknown parameter. So you just find what is the NP. So that we are giving as a 80 SCRs are in parallel. So if you come, this is this side, then 1 minus 0.1, that will give as a 0.9, and then 72 kiloamperes. The problem is given, 72 kiloamperes divided by n into 10 cube, 1 into 10 cube. That's all. So we'll get 80. And similarly, you can see that other problem. See, roll number 109. Why you are joining with some other mail ID?
I'm already through my official mail ID in laptop, sir. I'm connecting it with phone, sir. My laptop is dead and there's current gone. I'm with hotspot, sir.
That is fine, but if you are using same mail ID, automatically name will get same. Otherwise, you are giving something 109, no, that will not raise that. I told no, it is a formula based. If you
Okay,
change
sir.
that, will
I'll
not
join
be.
it through my official mail ID.
Yeah, preferably you do that. Otherwise, you will get absent. It is not
Okay,
my mistake. Now you can see that SCRs with rating 1000 volts and 200 amperes are available to be used in a string to handle 6 kV and 6 kV and 1 kV. Calculate the number of it is, I think, 1 ampere. Calculate the number of series and parallel units required. In derating factor is 0.1. So same problem, just you can see the derating factor is 0.1 case, 1 minus string efficiency. You just use that formula, then automatically you will get number of SCRs are in series is 7 and parallel is 6. So like that, any variations, the problems may be, many problems are there. You can see that this problem, derating factor is given 0.1 case, another derating factor is a 0.2. So that means that what you call it as derating factor changes, same problem, but what will happen? The number of SCRs is going to be differ. The formula is exactly same formulas. Derating factor consider 0.1, 1 minus string efficiency, voltage is given 6 kV, and each SCR rating is, you can see that 1000 volts, then we'll get it as a NP. The first case I got in series case, this is NS, this one is NS, this one is NP, because this is for parallel rating we used, this is a series rating used. Then we got 7 for NS, and then 6 for number of SCRs are in parallel. But now if I use derating factor is 0.1, we got 7 and 6. Now same problem, use the derating factor is 0.2. Then what will happen? You can notice this. I make use of derating factor, same data only. I increase that reliability. How can I increase the reliability? By increasing the number of devices. If it use more number of devices, it shares the less portion of the rating, then automatically reliability will be more. Instead of operating full load condition, if you operate low load condition, then automatically more reliable. That's what Instead of 7, if I increase the derating factor, you'll get it as a 8, and instead of 6, then we'll get it as a 7. So that is the derating factor. Similar fashion, I given some more problems also. Anyhow, I will share this. You can see, go through voltage across the SCR one drop, and you can add all these string. Each SCR drop, if I add, what will get? Total string voltage will get it. String voltage V1 plus V2 plus V3 and so on will get it as a string voltage. So like that. And what is the RC value? Same thing. Just voltage by that will give as a current. So discharging current based on that. So I given some more problems also. You just go through that. And now, if you want still more problem, you can refer in the Google book Power Electronics by my name. We have PHA publication. There I given still lot more problems also. You can go through, or any textbook you can refer for practicing purpose. But anyhow, I will give all these problems. I will share to you, and we'll go for SCR firing circuits. So this is one of the important topic. SCR firing circuits, how the device is going to conduct. That means that I need to provide as a firing pulse to fire the SCR. At what instant it is going to fire? That instant is a firing angle. The instant at which device is going to fire, that we call it as a firing angle or a delay angle. So for how angle is going to be changed, for that we require as a additional circuit. That circuit we call it as a firing circuit or triggering circuit. Normal circuit is a power circuit. Let it be, this is a one power circuit. I call it as a source is something AC supply. And if I connect some half wave rectifier or full wave rectifier or anything, then you can connect to the load. It may be R load or RL load or anything. This is the normal power circuit. So there is a power circuit or a power electronic circuit, anything you can call it as. And to fire the device, what we required is additional circuit is required. That additional circuit, I call it as a firing circuit or a triggering circuit. So this firing circuit I am going to explain now. So if without this firing circuit, the devices will not conduct. If devices will not conduct, we don't get any output voltage. So in any power electronic circuit, we required as a two circuits. One is a power circuit, another one is a firing circuit or a triggering circuit. So, and that triggering circuit also not only one instant, whatever instant you want to fire, at that particular instant you can able to give the firing pulses. So that is going to be as a firing circuit. Now we'll see that different schemes are there, different methods are there to give the firing pulses to the SCR. That we'll see one by one. That is a switched off to on state. We required as a several ways. What we have in the previous version in the turn-on methods. What are the turn-on methods? Forward voltage triggering, dV by dt triggering, temperature triggering, light triggering, gate triggering. All these 5 methods are available. But forward voltage triggering is not a preferable one. The voltage may be increases beyond the breakover voltage. There is a chance of getting that. That will be as a problem. So that's why generally we don't use that forward voltage triggering. And dV by dt triggering is a unwanted triggering. Whenever supply is given, then rate of change of voltage will increase beyond the specified value, that is a dV by dt value. Automatically device will trigger. Now it is not in your control. That's why this dV by dt also not preferable one. And third one, there is a temperature triggering. This also not preferable one. It is unwanted triggering. Reason is junction leakage current at junction J2 that leads as the temperature rise, and then resistance offered by that junction will be minimum and go on. It draws more current and cumulative process finally. If it reaches more than the specified temperature limit, then the junction J2 is going to be breaks down. So that is also unwanted. Then light triggering and gate triggering. These are the preferable method. In light triggering and all, very accurate. You can do it in the series operation of SCRs and all. All the devices have to be fired at the same instant. If it deviate one SCR maybe turn on time is more compared to other, like that. If any problem arise, then automatically there is a consequent string failure may takes place. That's why for that accurate turn on process we can use as a light triggering. In general applications we can use as a gate triggering. Nowadays microcontroller code or FPGA code you can write to generate the firing pulses and all, that is also available. But now as per our syllabus we need to discuss how firing pulse is going to be generated using our different method. Instant of turning on the SCR cannot be controlled by the first three methods, that means forward voltage, dV by dt and temperature triggering, and only the requirement is either light triggering or a gate triggering. Light triggering used in some applications, particularly in series connecting strings, and gate triggering most common method to turn on the SCR. So because of that, so accurately for turning on the SCR at a desired instant, we can use as a gate triggering. So now that methods we can effectively use and reliable method to give the firing pulses at what instant. It may be from 0 to 180 degrees. That is our firing angle range. But some of the methods may not be control up to 180 degree. That is a drawback. That's why to overcome that method, we'll go for as some other method. Like that, we have different methods. We'll see that firing method or triggering circuits both are same. Don't confuse in exam. Some cases they ask that explain the firing circuits or triggering circuits, both are same. Now there is a division R triggering. This is one of the method. We have 3 or 4 in sub classification also there. R triggering, then RC triggering. Some drawback is there in the R triggering. To overcome that, we will go for as a RC triggering. In that RC again we dividing as a 2 parts. One is a RC half wave triggering, another one is a RC full wave triggering, and third method is a UJT triggering. So using UJT you are going to fire the device, that is a UJT triggering. In that we call it as a synchronized UJT or a ramp triggering. In general, normal laboratory experiment if you want to do, preferably will use as a ramp triggering. Above 2 methods, that is a R triggering, there is a drawback. RC triggering, in that RC half wave is having drawback. To overcome RC half wave drawback, we are using as a RC full wave triggering. And again, for the better performance, we'll go for as a ramp rate triggering. So all this comes under this topic, that is a SCR firing circuit. It is important question. They may ask any one of the method. They don't ask all the methods. Circuit waveform explanation only. You can see either you can go for R triggering or RC triggering or a UJT triggering. Any one they may ask in exam. Now you can see this is the triggering circuit. That is R triggering means resistance triggering. RC triggering means resistance and capacitance triggering. That's the reason simple word will mention R and RC triggering like that. So in a resistance triggering circuit will be like this. You can see our intention is what? To fire this device, that's all. This is our power circuit, or you can say that in a power circuit, main SCR is there, that is a thyristor 1. To fire that SCR, we required some additional circuit to pass the pulse. Here what we are doing is just I am explaining this. Anyhow, theory part also I given consequent slides, but whatever I am going to explain, that is only in the theory part. Now we can see supply and some load, and this is our main thyristor. Let it be, I have to pass some signal to this device to trigger the SCR. So what is that? 2 ways. One way is I already explained in the previous introduction class. Either you can pass gate current, that is a IG current, through gate terminal. That value must and should will be IG minimum. If you pass the gate current below IG minimum, device will not trigger. We require anode to cathode voltage up to VBO. That is a forward breakover voltage. That much voltage is required to trigger the SCR if you pass the gate current less than the IG minimum. That's why at least IG minimum current has to pass through gate to turn on the SCR. Otherwise, maximum allowable gate current is IG maximum. You should not increase the gate current beyond the IG maximum. In between IG minimum to IG maximum, at any value you can able to pass the through gate terminal. So that we can say IG minimum we have to pass. That is one way. Other way is to trigger the SCR, there is alternate option is you can pass the firing pulse. You can connect that pulse across gate and cathode. Then also SCR is going to fire. And third one, we can pass the voltage across gate and cathode up to VGT. VGT is nothing but a gate triggering voltage. To fire the SCR, we need to connect gate and cathode up to VGT. Triggering voltage is to give. In turn, it pass through the IG minimum. If you apply gate and cathode some voltage, here you can see that some voltage, if I connect gate and cathode, that value must be VGT. Then also, in turn, the current will pass through the gate is IG minimum. The device is going to be triggered. So these are the ways are available to pass the signal to gate, either IG minimum, or you can pass the pulses directly, or you can give the voltage across gate and cathode. Using any of these three possible ways, you can able to fire the device. And at what instant it has to fire. That decided by when you want to pass the IG minimum. Suppose I want to fire the device at 30 degrees of delay, then at 30 degree it has to pass the IG minimum, or if 60 degrees, at 60 degree it has to reach a IG minimum, like that. Whatever the instant you want, for that particular instant you have to give the firing pulses or current pass through the gate terminal. Now for that there is a variable knob is required to change that alpha value. I want some instant 30, some maybe 40 or 50 or 60, anything. So there is a provision need to provide to change the alpha. For that we required as some additional circuit. That additional circuit portion is this one. This portion is required to pass the IG minimum. Here our intention is to pass the gate current, that value must be as a IG minimum. So in that you can see, now we'll see the explanation part. These are the waveforms. This one is circuit and this one is the waveform. Now how the device is going to be triggered. So during positive off cycle, let it be, this is a phase and this one is a neutral. And during positive off cycle, what will happen? Diode is forward bias or not? You can see this supply is connected to diode. So diode plus is connected to anode. That's why diode is forward bias. Minus is connected to cathode. Then diode also forward bias. And thyristor also forward bias. You can see plus is connected to anode and minus is connected to cathode. So what will happen? Thyristor is forward bias and diode also forward bias. Now we can see simple logic here. I want to pass the current. How much current? IG minimum. Now the instant during positive off cycle, thyristor is forward bias, diode is forward bias. Whenever supply is gradually rising, then what will happen? Current pass through this gate also gradually rising. Whenever current pass through that is gradually rising, then we can see that some instant current will reach us to IG minimum. At what instant? That will be decided by the resistor value, RV value. Let for this instant, you can remember R minimum, I need to fix this, or I need to insert some constant value. I will explain why that R minimum also. at moment consider R minimum is fixed one, RV is a variable one. Now, if I keep RV value some value, then we required to reach IG minimum some voltage. What is that voltage? Is a supply voltage. Now you can see that gradually supply voltage increases at some point of time. At this point, let it be current I is equal to V by R. V is this magnitude. R is fixed one. R minimum is fixed. See, I want IG minimum. Just carefully understand. I want IG min. Some value, let it be. And that formula is voltage by R min, that is a fixed one, plus RV. Now, I know R minimum value, let it be, it is a fixed one. And RV value, it is a variable one. First instant, I given as a something 2 ohms, just for example. Now, RV is a 2 ohms. And IG minimum also you known to you, because SCR rating is known to you. So I want I minimum value is, let it be 1 milliamperes current I required. Then you can easily notice that at what value of voltage I can get 1 milliamperes of current. Simply voltage is unknown here. Now we can calculate voltage. V is equal to 1 milliampere into R minimum value is something value, let it be 10 ohms or whatever. Just values are all random value, just for understanding. 10 ohms plus I fix that RV value the instant 2 ohms. Then how much voltage I need, you calculate. Once that voltage reaches, automatically this will reaches as the minimum, the device will trigger. Now it will be close the switch. If the device is closed, then what is the load voltage waveform? Where it is connected? One point is here, another point is here. No, this is directly connected across source, because see that the load, this point is directly connected here and other point is directly connected here. Then voltage across the load is same as the source voltage once device is on. That's why I made it device is on, voltage across that is equal to same as the source voltage. And then what is the voltage across the device? Because it is on, across the device is 0. And before from 0 to alpha, device is off state, no, because it is not reaches to the IG minimum. That's why device is off state. Then output voltage is 0. And but what about voltage across the device? Off state means same as the source. This portion you make it as a across this. Now I don't want to turn on the device at this instant. I want to turn on the device some other instant. So what is that instant? You can see, instead of here I want to fire something other instant. Now we can see that instead of that point I want somewhere else. Let it be here I want to fire this. Then what I have to do? I need to increase the RV value, because IG minimum is fixed, R minimum is fixed. Only possible option I have RV value. Instead of 2 ohms, if I keep 3 ohms, then what will happen? If I increase the resistance, you need more voltage to get 1 milliampere of current. That more voltage, instead of here, you may be required somewhere else here. Then at that instant only we can get IG minimum. Then your voltage waveform will be like this, and so on. This will be like this, and it will be short like this. And how long it will be conducting? Once again, if it reaches to the pi, natural zero will occur and thyristor is going to be open. So like that, we can able to control the output voltage, output voltage as well as the firing angle by controlling the RV value. Suppose if I keep RV value is very large, then what will happen? The required more voltage means maximum available voltage with you is only E maximum. So beyond that I can't get it. So that's why if I keep very large voltage, device will never trigger. That is the one problem if I keep RV value is very large. So another problem we can see here, if I am not using R minimum value, what will happen? R minimum is not there, let it be as a zero resistance, let short. I don't use that R minimum. And unfortunately, RV value is very, very low. Then what is the current pass through the gate? Gate current I is equal to V by R, no? R is very, very less because only the junction resistance is there. I am not using R minimum value, and RV value is unfortunately 0. I kept very low, and then very high current pass through the gate terminal. That's why I have to use one R minimum value. Otherwise, it may get current pass through the gate beyond the specified limits. That's why I keep R minimum value. That is a fixed value. What is that fixed value? R minimum must be greater than or equal to what is the maximum available voltage? V max or E max by what is the allowable current? Ig max. With that relation, you have to fix that R minimum. Now the problem we can overcome, even if I keep RV value with 0 also, because of the R minimum we already inserted, it never goes the Ig current beyond the maximum current, because I use that formula R minimum value such a way that we can able to make it V max by I maximum will be always greater than the R minimum value is equal to this ratio. That's why it never getting as a very high voltage, high current pass through that. That is the reason I keep that, and this RV value is used to get the variable voltage, variable alpha. That is the purpose I used as RV. And one more problem you can see here, this magnitudes, voltage magnitude after 90 degree, same will repeat, this voltages are equal to this voltages. So that is the reason after 90 degree device will not be fired. This control range is only up to 0 to 90 degrees alpha. Why? Because this instant is the same as this instant is same as here. That's why this magnitude and this magnitude is same. That is the reason this is going to be controlled only up to the 90 degrees instant. So that is the major in this lot of drawbacks are there. One drawback is control range is only 0 to 90 degrees, and another drawback is control process is by variation of the resistor. Once if I use the resistor, then automatically power dissipation is going to be takes place. And what is the function of diode here? Diode will prevent the negative pulses. So because during negative up cycle, if no diode, what will happen? Negative current pass through the thyristor. But during negative up cycle, thyristor should not fire. Thyristor has to fire only during positive up cycle alone. But once if you pass the gate current negative cycle also, it is unwanted. That's why power dissipation is taking place in a gate terminal. To prevent negative current to the gate, we can able to use the diode. So if the diode is there during negative off cycle, diode is reverse bias, therefore it won't go any current pass through the gate terminal. That is the purpose I used as a device. And other resistor I used as RB, that is a damping resistance, that we can see that voltage across that resistance should not be beyond, that is a protection, beyond the breakover voltage, or you can say that VGT. There is another word, gate triggering voltage, that we call it as VGT. If voltage across gate and cathode is equal to the VGT, then also device is going to be triggered automatically. To prevent that, what we need to use is RB, that damping resistance. If I use, that will minimize the voltage drop across gate and cathode, or voltage across gate and cathode is always less than the VGT. Therefore, it won't be trigger. Our intention to use this circuit is whenever you want to fire the device, at that instant the pulse as to pulse means here as a gate current has to pass, that current must be as IG minimum current and the device is going to be trigger. That is the process. Now you can vary the RV, you can able to get it. So this is your R triggering. If the circuit and waveform is correct, then explanation is very simple. One, why we are using R minimum and what is the RV and why we are using diode, all these things. And simply you draw the circuit. Whenever if IG minimum reaches, SCR is going to be fired and you want to change the alpha. The instant at which the IG minimum is reached is depends upon the RV value. You can change the RV value and automatically conduction is going to be changed. So like that you can explain. And drawback also you can explain. What is the drawback? Control range is only 0 to 90 degrees. And another one, it will give only the during positive half cycle only we are getting the output voltage, that we can overcome later methods. And another drawback is the power dissipation is going to take place because we are controlling through RV. So these are the some of the drawbacks. That all points I mentioned in what you call it as in the upcoming slides. This is the theory. And now you want different alphas graphs also you can plot it. In exam, it's not required to draw all the plots. They based on the question. Any one plot you can draw and you can explain that. So now here what is the problem we can notice? If I keep that voltage is less than VGT, device will never trigger. Gate and cathode voltage is less than the VGT, device will not trigger because it is not minimum voltage is required is VGT. If you apply gate and cathode voltage less than VGT, it never trigger. So automatically output voltage is 0 because SCR is not fired. And what is RV here? I can use the less value of RV and I can use the high value of RV. What is the difference of less and high value? Based on RV value. If I keep RV value is high, you will get alpha will be more. More alpha means higher alpha will trigger the SCR. RV is less. So less resistance means it will reach the IG minimum is a less voltage. So automatically it will trigger the SCR with the starting instant, that we call it as a less alpha. So now I run the waveforms different RV values also. Instant and then current waveform, voltage waveforms are same and voltage across the device. Hello? Hello? I'm audible?
Yes, sir.
Okay. Here now we'll see that different RV values you can able to get it as a waveforms will be like this. Just for understanding, I make it as a different values of R. That waveform we can analyze. Here you can see that if R value is less than 90 degree means exactly 90 only will get it. Beyond 90 that values are repeating. That's why it won't be trigger that. So this is the different variations we can able to get that waveforms are differently. So now we can see other triggering method. This is what theory I given, all whatever operations are there. So this is already explained. It's not required, only for your reference I make it as a slide. So how much value of resistor I have to use? R minimum must be greater than the E maximum by IG maximum, and what is the damping resistance I have to connect. So this RB is always less than the VGT. So that is based on our circuit. This is the formula I have to use it, resistance triggering and all. And another one is what is the supply voltage, that must be equal to, there is RV and R minimum, that is the resistance, pass through the gate current is IG minimum. plus voltage drop across the diode and VG minimum. So this is the supply voltage formula. So you just while you are doing the problems, you may be required this equations that you can remember based on your normal equation only. Supply and passes through the R minimum, then RV, and it is goes to the VD. VD means diode drop across that, and then gate. That is the sequence. That's why I mentioned this drops, all the drops, that is equal to as a source voltages. So what are the disadvantages? This also I explained. Triggering angle alpha is greatly depends upon the Ig minimum. At what instant it is going to be occur, that decided by the Ig minimum value, that means RV value. So in turn, I want to change the RV to get it as a Ig minimum. That is one drawback. And other drawback, you can see that because of that supply voltage dependency, that is going to be a repeat after 90 degrees. Whatever magnitude is there, supply magnitude from 0 to 90, same values will repeat from 90 to 180 degrees. That is the reason if I keep that RV value is more and more, I don't have the higher magnitudes after 90. That is the reason it will be control only 0 to 90 degrees. This is the major drawback in the R triggering. And another one, there is a load voltage waveform can only be varied from 0 to 90 degrees. That is the thing. Now we'll see some of the problems also. That is we'll see that design R triggering circuit for a half wave controlled rectifier circuit for input voltage is 24 AC supply. SCR to be used as the following data. What is the Ig minimum is given, Ig maximum is given, Vg minimum is given, and Vg maximum is given. So what are the parameters we need to design? That is the circuit, same, that circuit and this circuit is same. Supply, load, and then this R1 means R minimum, this is a fixed one, RV is going to be vary, and this is a damping resistance RB, and then there is a some book is given like this circuit, and this is a PS Bimbra is mentioned like this, because in problem they may give any circuit only to show that circuit same as R triggering circuit only, and voltage across that SCR, that is a VT. Now what is the VM? Vs into root 2. You will get it as a R minimum. How to calculate? I given as a formula in the previous slide. You can see that 1 is a minimum according to our circuit. R minimum notation I use, that is equal to max or E max or V max divided by Ig max. Ig max is our allowable maximum current, gate current. So R minimum you can easily calculate because parameters they ask you to calculate. So R minimum, that is equal to V max by Ig max. What is the V max? Vm. So what is Vm? Vs is given 24, no? Vs into root 2 will give as a V max. What is the Ig maximum is given? 12 milliamperes. So I mentioned 12 milliamperes. So then the value is 2.8 kilo ohms. So according to our resistors, availability resistors, 2.8 or 2.9 that kilo ohms resistors are not available. That's why that is equal to 3.3 kilo ohm resistors we have to use it. That is the first parameter we design. And another one, RB. This drop should not be greater than the VGT, gate triggering voltage. So that formula, as previous slide I mentioned, Vg max into R minimum by V max minus Vg maximum. So that formula you can see that 1.5 volts is given, Vg maximum is given 1.5 volts, and R1 value just now we calculated. This is the R1 value, and divided by V max, Vs by root 2, Vs is 24 into root 2 minus Vg max. That voltage also given, Vg max is given, that is a drop across that SCR, you can say that 1 to 1.5 volts. So if it is not mentioned also, you can take it that is, it's given, Vg max is given 1.5 volts. So you just substitute that, we can get it as a 120 ohms of RB. And then R2, what is the R2 here is a variable resistance. In our case, the notation I mentioned as a RV, that is a variable resistor. So how to calculate that R2? We can see that divider rule. So there is a VG min by V max minus VG minimum, that is equal to R by R1 plus R2. Then we can get it as a what is the value of R2. So if we substitute this data, we'll get 3.37 kilo ohms. So there is a drop across VD given as a formula in the earlier VD also. Vs is equal to something formula I wrote, no? So that is R1 into R2 into Ig minimum plus Vd into Vg drop. So all these things are mentioned here also, but diode drop is neglected, because in some problems they may given Vd is equal to 0.7 volts or something. We can add that also, otherwise you just neglect that. So then finally we'll get it as a 3.37 kilo ohms. So these are the some of the formulas we can mention, and we'll see on the next class RC triggering and UJT triggering and ramp triggering methods, and then that is one complete topic, triggering circuits of a SCR. So if you have any doubt, you can ask me. And afternoon I will take the lab session. I will open the MATLAB and I will connect and I will explain the first experiment, and we'll see. After that you have to practice. So today power electronics lab, all 60 members will come to the power electronics. In the next, I think preferably my session is on Friday. On Friday you will get EM2 lab as usual schedule, and only thing is exchange that Friday slot to 2 days. So I will take a 2:20 afternoon power electronics lab. You can join there. Anything? And tomorrow first hour I will take the power electronics class. Instead of Thursday, my hour is there on Thursday. I will take tomorrow first hour. And Thursday you no need to come. If you have any doubt, you can ask me.
No, sir.
You got it now? Afternoon is power electronics lab. I think I shared the link also.
Yes, sir.
Yeah. Okay, fine. Tomorrow first hour also power electronics class. Now you can leave.